Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Middleware system for managing these distributed devices, and in particular devices that's owned by zebras roaming around in the Kenya National Park. And I think the picture actually shows the example of that. So with that, Ting.
Thank you. Thanks everyone for coming. So this talk is about my thesis work on the middleware system on sensor network. So in recent years, sensor networks has emerged as a domain of distributed computing with heightened importance and interests. Sensor networks are typically comprised of many sensors distributed across the environment. Sensor nodes have sensing capability to gather the environment information. They have also limited computation and communication resources to communicate the data and process the data throughout the network towards a centralized base station. If the base station is interested in some specific, let me try the laser pointer. If the base station is interested in some specific information, it can also pose a query into the network and draw back the data with the matching attributes. So overall, sensor systems are long-running computer systems. So long-running autonomy is a very important system requirement. ZebraNet is a mobile wireless sensor network. It is used to improve the tracking technology through energy-efficient tracking nodes and store and forward communication techniques. Specifically, we want to track zebras in Kenya. They are wildlife zebras. And we want to help the biologists to understand their movement patterns, interspecies activities, and the impact of human development on their behaviors. While ZebraNet's immediate focus is wildlife tracking, its broader goals concern the communication, deployment, and management issues for a large scale of both static and mobile sensors. A ZebraNet hardware node contains the global positioning system to acquire the position data for wild zebras, and the microcontroller CPU to process the data, non-volatile flash memory to store the data, and wireless radio transceiver to communicate the data. ZebraNet does not count on constant access of communication with the base station or other sensor nodes. Instead, we use periodic node discovery and node-to-node communication to propagate the data throughout the network to a centralized base station. So compared with other sensor networks, ZebraNet has higher node mobility because zebras tend to move a lot. And our communication device has longer range because we need to connect sparsely located zebras in a wide range, typically hundreds of square kilometers. And our sensing device has higher power consumption. And finally, our network is designed to be deployed for a longer period of time because we have very restricted human access to the wild animals. So overall, we feel like ZebraNet is a good study example that fuses the sensing system characteristics with mobile computing technologies. In this talk, I will first give an overview on the ZebraNet project, including its application goals and hardware constraints. Then I will introduce Impala, which is the middleware and OS layer of ZebraNet. I will spend most of the time talking about its architectural design and implementation choices. Finally, I will conclude this talk with a contribution of this work. In terms of application, currently, the major applications running on the sensor nodes of ZebraNet are the communication protocols that work to gather the local position data for zebras and propagate the data to a base station. Because our network is so sparse and disconnectivity is so common, we depend on store and forward communication styles. To do that, nodes periodically wake up and look for network neighbors. Imagine that at some point, node A and B finds each other in the network, And so they will exchange data so that A will have B's data and B will have A's data. Potentially much later and far from node A, B will see another node C, and they will exchange data again. Eventually, the biologists will drive a car or fly an airplane into this area, and they can collect data from a single zebra to get the data from multiple zebras from previous communication. So there are several key issues that the application design need to handle. First of all, in the previous scenario, most of the nodes will perform symmetric transmission in data exchange, and they will duplicate their data copies whenever they see other zebras. However, we're also looking at more selective and asymmetric transmission due to energy reasons. And we're also looking at strategies that can reduce the number of data copies injected into the network due to bandwidth constraints. For storage management, the applications need to determine the appropriate policy of prioritizing a zebra's own data and other zebras' data. And they need to have an efficient way to find out which data has been delivered to the base station and so can be evicted from the local storage. In the future, we also plan to put on more sensors, including like image sensor, heart rate sensor, body temperature sensor, and accelerometer, stuff like that. So that means we need to adopt more advanced applications that can handle a larger amount of data by data filtering and fusing, in addition to data communication. For ZebraNet hardware design, the picture on the left shows the board layout with the major components. And the picture on the right shows the tracking collar we built when it was put on the wild zebra. You could see the black dots are the solar cells because we use solar energy to power the board. This block diagram gives you some more details about the hardware design. Specifically, to process data, we have a microcontroller CPU. It has 2 kilobytes of RAM and 60 kilobytes of ROM. It can run off of an 8 megahertz clock and a 32 kilohertz clock. To acquire the position data for zebras, we use a GPS module. Its typical position fix time is 10 to 20 seconds. To log the position data, we have a flash module. It has 4 megabits of capacity, which is sufficient to store 78 days of data from a single zebra. And to communicate the data, we have a radio module. It has over-the-air baud rate of 19.2 kilobit per second, and its typical transmission range has been observed as half to 1 mile. And other than the major components, we also have power supplies, charging circuits, and solar modules. So this table shows you the power measurement of the system when the system is running at different modes. In particular, when the CPU is running at 32 kilohertz clock, it consumes half as much power as when it's running at the 8 megahertz clock, and so can be used as a low power mode. This hardware design has imposed several important constraints on the system software programming. I will talk about how we deal with these constraints in later part of this talk. So after introducing the background of this project, now comes my thesis work. I have been focused on building an efficient middleware system for sensor networks. The motivation for a middleware system for sensor network comes from the opposing needs of sensor application development and the sensor hardware realities. On one hand, sensor applications need to be simple to program. They need to be modular for the ease of upgrade, and they need to be autonomous for the long-time system deployment. But on the other hand, sensor hardware has very stringent energy budget. They have low capabilities and limited resources. So the first requirements calls for special middleware support for the application development. The lower part calls for careful layering system design. So my work is to investigate how to build an efficient middleware system to reconcile the opposing needs by sensor application and sensor hardware. we were facing a number of research questions when designing the middleware system, including both architectural questions and implementation questions. The first question is, what services should it provide? In contrast with some existing sensor network operating system approach that is very lean and provides very basic and limited service to applications, I built Impala that serves as the middleware and operating system layer for sensor network, but also has been designed to achieve application simplicity, modularity, adaptivity, and repairability. Specifically, the design of Impala has been driven by several important issues in sensor network operation and deployment. First of all, because sensor networks usually is of large scale, coordinating the computation and communication across many nodes is complex. Over the lifetime of the system, you may encounter a number of different scenarios, for each of which a different communication or computation strategy may be more appropriate. So some amount of adaptivity is crucial for the network performance. Second, it is inevitable that software update will be required over the lifetime of the system. However, because sensor networks are often deployed in large areas that is inaccessible to human being, so it's impractical to do manual updates. In ZebraNet in particular, we cannot afford to tranquilize the zebras each time we have a software update to apply. So that means we need automatic software updates so that software updates can be plugged in at any time. Next, data gathering is the primary focus of sensor networks. As a result, sensor nodes often use aggressive flooding strategy to maximize the chance of finding a path from each node to the base station. As a result, multicast and broadcast is common communication patterns. Transmissions are required to be reliable if data integrity is critical, but may not be reliable for energy reasons in other less critical uses. So we need to provide sufficient network support for this variety of network communication styles. And finally, sensor networks is designed to run for a long period of time without human intervention. Many sensor operations occur in a predictable timetable, so we need clean mechanism and reliable mechanisms to schedule these recurring operations. Sensor networks are also driven by irregular events, such as sensor data capture and network data reception. They are frequent and concurrent and may have different time constraints. So we need clean mechanism to efficiently handle these various events. The various services provided by Impala can be categorized as the middleware part and the operating system part. For the middleware part, it includes the software adaptation and update. It has been prototyped on HP iPAQs. For the operating system part, we implemented on the real ZebraNet hardware node, including the operation scheduling, event handling, and network interface. So for the middleware part, I will describe what are the challenges and how we solve them. For the operating system part, I will describe, in the context of the implementation experience, what are the impact of the underlying hardware realities to our design choices. So the next question is, excuse me, how much layering and what interfaces should it have? Again, in contrast to some existing operating system approach that encourage deep layering of abstract components, we feel like deep layering can generate significant overhead in the low capability and resource-constrained sensor networks. So instead, we adopt a three-layer simple system architecture. In this architecture, the top layer is the application layer that contains all the application protocols that currently work to gather the position information of zebras and propagate to the base station. The middleware layer is the Impala layer that implements different middleware services. The bottom layer is the firmware layer that contains all the firmware modules to manage the hardware devices. Three interfaces in between these layers. The downward arrows represent the service interface. Specifically, the firmware layer will export all device accesses and controls to the Impala layer. The Impala layer instead will prevent the application from directly using these interfaces, but rather only export a number of services that is necessary in a reduced and protected form. The middle one is the event interface. Specifically, the firmware layer exports a bunch of raw device events to Impala. Impala will capture these events, further process them, and dispatch them to different system components. The applications are all programmed into a set of event handlers that will be invoked by Impala when the associated events is received. And the last interface is between the middleware layer and the application layer that is used to achieve software adaptation and update. This graph shows the memory footprint of the different system layers. Remember that currently we only have 60 kilobytes of code memory and 2 kilobytes of data memory. And currently our system consumes about 1/3 of the entire code memory, and our static data consumes 1/6 of the entire data memory. So that leaves sufficient space for future system expansions.
Excuse me.
Yes?
Does that include all the other animal data that you said you store locally? Is that just, so what data is that?
So the data is the resource allocated to make the operating system and application work. The data, the Zebra data, is stored in the external flash memory.
Okay, so that's not
Yeah,
animal
it's
data.
not
Okay.
part of it. So the external flash memory is like 4 megabits of capacity. The next question is, how do we achieve application adaptivity? There are two scenarios where adaptivity is desirable. First, as the energy efficiency and performance of applications heavily depend on the number of parameters in the system, the application adapter wants to handle an interesting range of parameters to achieve the best performance. In ZebraNet in particular, our goal is to study the movement and behavior of the zebras. However, the actual movement and behavior pattern is very important to the communication performance of our applications. So without that data, it's hard to determine what kind of strategy should be used. Instead, we provide multiple application choices and adapt among them when in the real deployment experience. So our approach is for applications to track a number of parameters. The Impala adapter will use the timer event to periodically query the applications for the parameters. Once the parameters satisfy a predefined rule, an application switch will happen. The second scenario is to adapt when a device failure happens, but I will skip the details for that part. To give you an example of how adaptation should happen, currently we have developed two application protocols for ZebraNet. One is a history-based communication protocol, in the sense that each zebra will transmit to only one neighbor in the network out of a group of neighbors. And that neighbor should have the best score of delivering the data to the base in the past history. This protocol will be efficient when the network neighbors is, you have lots of neighbors and the network connectivity is good. But when zebras are far apart, you may prefer to use a more aggressive flooding strategy that transfers to every network neighbor within range. So an interesting question here would be, what if the network connectivity is actually a hybrid model, with some nodes clustered together and others at remote distances? So to study this problem,
You say sent to just one neighbor. Isn't that are you presumably broadcasting with a radio? So are other nodes
Yes.
allowed to pick up the information?
Yeah, you send the data through the wireless radio, and you broadcast to everyone, but only one will be receiving that data, because if everybody is receiving data, you are actually duplicating the copies.
More worried about copies than
Yes, because
transmission power.
Because if other people receive the copy, then they need to forward the same data. It's using their bandwidth and it's using their storage. And so it costs energy and storage capacity, both. So to study this problem, we conducted simulations. In this simulation, we put 50 zebras in an area map of 20 kilometers by 20 kilometers. Each node is able to schedule 2 different protocols. One is the history-based, one is the flooding. And the mobility model is followed by some preliminary data provided by the biologists. So in this graph shows the data homing success rate of different communication strategies when the radio range is varied from 100 meters to 9,000 meters. As you could see, when the radio range is low, flooding is better than history-based, because by sending it to everybody, it maximizes the chance of finding a path to the base station. However, when the radio range is high, excuse me, when the radio range is high, flooding is outperformed by history-based, because by duplicating too much copies into the network, flooding becomes constrained by the limited network bandwidths. So based on this observation, we adopt a switching strategy that uses history-based when the number of network neighbors is high, and use flooding when the number of network neighbors is low. And this graph shows that the switching curve is even better than both non-switching curves at some medium radio range. At this radio range, the network is really a hybrid model with some nodes clustered together and other nodes at remote distances. And so that further demonstrates that our adaptive strategy can really pick up the appropriate strategy for the specific local networking condition. The next question is, how do we efficiently reprogram the sensor network with software
Can I ask a question? What's
Sure.
the policy for throwing away data when your buffer gets too big? Presumably that's why it eventually fails.
Yes, that's a good point. And I mentioned in some previous slides that currently we are looking at the policy to prioritize one zebra's own data and the copies from other zebra. So currently we have statically allocated flash memory section that only holds my data. And once that gets full, you will evict very old data from the beginning. And we also similarly have another flash section that store only data from other zebras, and we use the same policy for evicting data. So to answer this question, as I mentioned before, it is inevitable that software updates will be required over the lifetime of the sensor network. And we cannot tranquilize zebras for software updates. So the basic idea here is to broadcast updates wirelessly through the radio transceiver. For example, when the software updates first show up in the network carried by a sensor nodes, it will broadcast to all the network neighbors throughout the network until the entire network is reprogrammed. However, there's some specific characteristics in ZebraNet that makes this problem more challenging. First of all, in ZebraNet, nodes have very high mobility. And second, in ZebraNet, data is frequently collected by the sensor nodes and will be eventually delivered to the base station. This generates significant amount of data traffic and leaves the bandwidth for software transmission even more constrained. And finally, in ZebraNet, we envision a wide range of updates. Could be small bug fixes, could be major application improvements, or it could even be deleting or adding an entire application. So these special challenges make us think about that application updates need to handle some advanced issues. First of all, incomplete updates will be common because the transmission can be terminated at any time when the bandwidth is used up. And the connectivity can be broken at any time when zebras moves apart. So it may take several attempts to get the entire complete application updates. And second, incomplete updates cannot be immediately loaded into the system for execution. This is because we have a wide range of updates. The updated part may be incompatible with the non-updated part. So you have to collect the complete updates for execution. And finally, because the time for one software update to infect the entire network may take a long time, when updates are issued close to each other, nodes may receive several updates, and some of them may be out of order. So to deal with these issues, we have a special software management mechanism and software transmission mechanism. For management, we divide each application into software modules. A Zebra needs to collect all the modules before loading the application. That means we can actually collect only the changed modules and reuse the unchanged modules to save the amount of network transmission. To be able to find out which modules has changed from the previous version to the current version, you need more version information. So we associate an application version number with the version numbers of the enclosed software modules. By advertising this software version information, one can perform selective software transmission. We designed a 3-stage on-demand software transmission mechanism. In this mechanism, each node will store one complete version of an application and several incomplete but higher versions of an application. For example, for Node A and Node B, Node A has a complete version 3.0, and Node B has a complete version 1.0 and incomplete version 2.0. So in the first stage, A and B will first exchange their version information. Then B will know, okay, A has a higher version. So in the next stage, B will send out a request to A, request asking for the specific modules from version 3.0, and record 3.0 has an incomplete version to receive. In the last stage, Node A will transmit to B the module requested by B. At the end of the transmission, B will mark 3.0 as the complete version and remove any incomplete but lower versions. This procedure will be repeated if the zebras did not send uniform software population, because that's a good indication that the software reprogramming procedure has not converged. Otherwise, the procedure will be exponentially backed off to save the number of network message exchange. So to demonstrate the efficiency of our network reprogramming strategy, we conduct another simulation. In this simulation, we evaluate two different update strategies. In one strategy, each node wakes up once every 2 hours and look at the neighbors, and they flip a coin. If the coin says yes, it will just blindly broadcast the software update to all the neighbors. The next one is our on-demand transmission, in the sense that nodes also wake up once every 2 hours, but they first exchange version information and transmit updates only when it's requested by some other nodes. So when the probability equals to 1, the probabilistic broadcast represents the ideal case because it achieves the maximum reprogramming speed. As this graph shows the time for one update to be infected throughout the entire network. As you could see, our on-demand transmission closely follows the ideal case and outperforms the probabilistic broadcast with lower probability. However, while achieving almost optimal performance, our strategy consumes much lower communication overhead. This graph shows the number of software transmissions performed in the same experiments. As you could see, Impala's on-demand transmission increased with the number of updated nodes, but the probabilistic broadcasting increased linearly over time. So the next question is, how can we support a broad variety of network communications that appear in sensor network domain? Sensor networks heavily depend on data exchange and processing within the local neighborhood. So communication within a single hop neighbor is the prevalent communication style. In many existing sensor network applications, we have seen a broad taxonomy of single hop message models. For example, because sensor networks often use aggressive flooding strategy, broadcast and multicast are common communication patterns. For another example, transmissions are required to be reliable for data integrity purposes, but may not require to be reliable for energy reasons. So to support this broad taxonomy of sensor network message models, Impala provide a network interface and implement the various message models with our network sessions. Each network session is a message that can carry up to 32 kilobytes of data by a sequence of packets. We use connectionless transport to send the network session because we feel like connection-oriented transport is a poor match to the unpredictable zebra movement. And we use asynchronous transmission for network sessions. Go ahead.
Does connectionless transport mean that one of these 32 kilobyte sequences might get picked up by a different peer? Or does it just mean that, if you need more than one packet to get done one of these transmissions of 32 kilobytes of data, then that's in a sense a connection, right?
The connectionless sense in our scenario is that we don't do the handshake. You just directly, once you find someone in your neighborhood, you just directly aim your data to that node without first saying hello and being acknowledged by the other side.
Yeah, but at some point, some of those protocols were definitely two-way because they required the receiver to acknowledge or to do something interaction to correct errors, right?
Yeah, so that's during the transmission you can use all kinds of methods to do.
So the only sense in which it's connectionless
is the established phase.
Is that you don't have the initial 2-packet handshake?
Yes.
Okay. We're talking about a sequence of hundreds of packets here, so is it? I guess is that an important feature?
Because when zebras move around very fast, even if you make a handshake, the connection can be broken. It's not like internet where you make a handshake, you know the other person will be there. So it doesn't give you any benefit to make the handshake. I think that's the major point.
That's directly proportional to power consumed, is that correct?
Yes, that's 6 hours.
How did you measure power consumption, and how did you mitigate the problem of, say, depleting a battery before it got recharged?
So I will talk about this power management mechanism in a little bit, but to make it, to summarize that, we basically check the voltage scale before we go into any power-intensive operation, such as radio transmission, GPS sensing, to make sure the system will not crash from insufficient energy.
How often does that happen, that you have to curtail that? And I haven't seen that as a coefficient or a metric in your determination of what node transmits to any other node. So that's yet another metric that you evaluate that could say, all right, you're a high priority node that's responsible for internode communication, but you can't transmit because you have a severe power problem. So do you have a way of mitigating that?
That's a very good point. But remember, in our system, the Impala provide the primitive communication interface. How the communication is performed is actually determined by the application layers, which are the actual communication protocols that transmit data. So there's some other people in our group are looking at the same issue. Basically, what are the appropriate energy efficient transmission protocols to use? So this graph shows the overhead for transmitting a packet out of a network session by different system components. As you could see, the CPU compute time to support the various message models is almost negligible compared with other overhead. Okay. We use unified media access and transport control to implement Impala's network interface. Because our system has ongoing access to the global GPS time synchronization is very easy to achieve in our system. So we use a static round-robin time slot mechanism for media access. This is designed for the simplicity of implementation, but also this allows us to know which packet has been lost, and so can perform retransmission in the earliest possible time. For example, imagine there are 4 nodes in the system A, B, C, and D. At the beginning, A sends a bunch of packets to B, C, and D. B received all of them, C received half of them, and D didn't receive anything. So in the subsequent time slots, B will send out a full acknowledgement, C will send out partial acknowledgement, and D will remain silent. So in the next round, A will know B was fine, C was problematic, and D was totally a failure. So A will resend the packets to B, C, and D. This time, B and D are fine, but C still have... Go ahead.
So I'm a little confused because if it's a connectionless protocol, how does it know that D is there? How does it know to expect an act from D?
So yes, that actually involves the application level neighbor discovery. So the application, so in ZebraNet, how it works is we first broadcast a hello message to all the network neighbors, and then we'll know who is around. Then I will use connectionless transport to transmit my data to the neighbor I want to have. So in the second round, in the third round, A will say, oh, I will just give up on C and continue to transmit the next bunch of packets. So this, by unifying the media access control and transport control, we are able to, go ahead.
I was going to wait to end your sentence, but so when you say static time slots, you mean one per zebra?
Yes.
How many zebras do we have? And how many of them are frequently nearby? I mean,
So in this, last January, we went to Kenya, and we deployed 7 collars on zebras.
Okay.
Next year, we plan to have a larger scale deployment in which we'll have about 30 collars. So the static time slot allocation will be fine for this scale of network. But if the network scale gets larger, we'll also consider contention-based and time slot-based.
Because I mean, it seems like one of your main resource limitations is bandwidth, and it seems like you're really tossing a lot of it out the window. If you can see, 2 neighbors out of a total of n, then you're only getting, 2/nths of your bandwidth, right? Because during one round, you're only going to use 2 of the slots.
Yeah, but one problem is much more energy is consumed on transmission. So if you're not finding other network neighbors, you're sitting there for receiving, you actually consume much less power than transmission. So the amount of energy wasted in here is not that significant. And considering that...
Right, but I thought, so the concern here is actually energy, not the bandwidth. I thought the limiting factor was that you only have so much bandwidth as the zebras pass by one another. And maybe you have enough energy in the battery, but...
Yeah, it's more of the energy, because if you have more energy to spend, you can have longer period of communication, then bandwidth will not be a significant problem. You can
unless the zebras leave, but okay.
Yeah, yeah.
ABCD, do you assume these are all the neighbors in the world you're considering? This is statically
Yeah,
scheduled
this is
beforehand?
just an example.
Or just the neighborhood of
This is all the world.
This is all the zebras. Okay.
So you have to know at deployment time the ultimate size of the network. You can't
Yeah.
add nodes after the network has been deployed.
Yes, that's why I said it's static around.
It's static for the whole lifetime of the network.
Right.
How wide are those time slots?
Currently, we're using 2-second time slots.
And your time base is from GPS, so everybody knows the same time?
Yes.
What about sleep time? That's pretty open loop?
Sleep time, you said?
Yes, I imagine you put these things to sleep and don't use GPS time to monitor how long you've been to sleep.
We use GPS to have time correction, and once we know the current time, we can schedule a sleep period for maybe an hour. So that period does not rely on the GPS, constant GPS time correction.
So you wake up at slightly different times and then you resync.
Yes.
But the guy who wakes up early could be transmitting to nobody, so he wastes power.
So that's why we have this global time synchronization through GPS. So every node, every zebra has the same time, and they will wake up at the same time. They will transmit and wake up at the same time.
But when he's asleep, when the device is asleep, you don't have an accurate clock. Right, your GPS is down, so all you have is ground truth or truth at the beginning of the hour sleep.
Yeah.
At the end, you may be off a second or two or whatever.
It would not be, the timer drift over this an hour period is not very significant. I performed some test experiments. Over a 40-hour period, the timer drift by the hardware oscillator is only about 5 seconds. So that's over a 40-hour period. So, and also a little bit time offset between nodes will not be a significant problem as long as we have reliable transmission to recover from garbled data. So by unifying the media access control and transport control, we are able to reduce data copies and overhead throughout the network protocol layers. Because we have memory constraints, reducing the buffering overhead is also an important issue. For example, on the transmission side, we have 2 kilobytes of RAM at the maximum. At the same time, our radio baud rate is 92 and time slot is 2 seconds. And so that means the data throughput will be throttled by the amount of data buffer we have. As a result, we're only utilizing 40% of the bandwidth. So instead of using data buffering, we use data indexing in the sense that no matter if the data is physically from the external flash memory or from the on-chip RAM, we always pin the location of data and directly copy the data from the physical location to a small temporary buffer for radio packet transmission. Similarly, on the receiver side, we have each network session can be as large as 32 kilobytes, but we have 2 kilobytes of RAM. That's only 6% of the entire session capacity. So instead of delivering the session or message to the application in its entirety, we also provide packet delivery in the sense that we deliver packets immediately to the application when it is received in order from the radio, while other packets in the same network session are still under transmission. So these two graphs shows the transmission side memory requirements for reliable multicast sessions and unreliable broadcast sessions with different number of destinations. And this graph shows the reception side memory requirement for different number of packets with different data size in the packet. Actually, because the speed for the microcontroller to process each packet is much faster than the radio reception rate. So over time, in typical situation, only one packet at the most will be buffered on the receiver side. Because our radio device provides us with the physical packet size of only 64 bytes, that means reducing communication overhead is also a very important issue. We cannot afford to use the traditional TCP/IP layered header protocol format. Instead, for example, if we have 8 destination addresses for the network session to transmit, the address part will compose 25% of the entire packet size. That's pretty significant. So instead of using this traditional layered header format, we transmit one full version of header out of each session only in the very first packet, but embed shorthand reference to the full version of header in all the subsequent packets. As a result, this graph shows the header size and the payload size ranges for different Impala network packets.
Where does the 25% come from?
So, for example, each time I'm sending one packet to 8 different nodes. In my header, supposedly you need to specify who I'm sending to.
Right.
So 8 node address will be 16 bytes in our system. Suppose,
Bytes?
yeah.
For
Each node ID is 2 bytes.
Well, not just a bit. Not just use 8 bits.
Sure, you can do that. But this just to give you an example that because address part is not the only component in the header, you could have other informations like the reliability of the data and how you want the receiver to handle the data. All this kind of meta information you don't want to embed all this kind of information in each of the packets you send. Instead, you only have this information transmitted once out of entire network message, which contains multiple packets.
So you're saying that in the header, so like you're broadcasting, and the header contains a list of all the intended receivers? Is that?
And other information about how to handle this session by the receiver.
Okay. So this is basically for multicasting, where you don't want to broadcast to everybody, but you don't want to resend multiple unicasts, so you're enumerating every receiver? Okay.
So the last question is, how do we manage the various system activities? As I mentioned before, we consider the sensor network activities to be composed of regular operations and irregular events. We want to achieve reliable operation scheduling for and an efficient event handling mechanism. For reliable operation scheduling, we first need to consider the energy constraints. Because we know what is the desirable sensing and communication frequency in our system, that also determines the desirable volume of the overall system activities. So it's unreasonable to make the system fully on all the time. We schedule the duty time and the sleep time. In the sleep time, we turn off all the peripheral devices and put the CPU in the low power mode. Basically, let it run at the 32 kilohertz clock. Also, to prevent the system from crashing due to insufficient energy, we also perform voltage check before any power-intensive operations. If the battery voltage is not high enough, we'll skip the radio communication or GPS sensing and directly go to the sleep phase. There's also device access constraints we need to consider. For example, due to voltage regulation challenges, the radio chip and the GPS chip cannot be turned on at the same time. So we define a separate networking phase and the GPS sensing phase to alternate the use of the two devices. This table gives you some typical overhead in operation scheduling. The overhead are mostly at hundreds of cycles, except some large numbers are caused by the specific hardware attributes. For example, to turn on the radio transceiver, you need to wait for 1 second for the voltage to be stable and for the radio to be fully waken up. Next, we want to achieve efficient event handling. In here, we want to deal with 3 different issues. First, because events are originated from various hardware interrupts, dealing with these interrupts will involve lots of hardware details and lots of programming efforts. So we encapsulate the miscellaneous hardware interrupts into a number of abstracted application events to simplify the application programming. The second issue is concurrency. Multiple information flows can be going on in a system, and sometimes the low-level processing may have real-time constraints and need to override the high-level processing. So we adopt a hierarchical model to process these events, in the sense that we use a single thread to process long and preemptive software events, but at the same time, that thread can be interrupted by short and atomic hardware interrupts. The third issue is we want to achieve event prioritization. Different sensor network events may have different time constraints. Some may need immediate processing, but others may have tolerance to high delays. So we put different events with different time constraints in the event queues and process them in the desired order. This graph shows you some example event handling overhead in handling a packet reception event by different system layers. In particular, the firmware layer is responsible for generating the events, basically process the bytes in the packet and deliver that packet to Impala layer. The Impala layer is responsible for filtering the events by further looking at the packet and determining which packet it should deliver to. Then eventually, the application will process that event by writing to the flash memory and some other related computations. As you could see, comparing with the actual event processing overhead, the overhead for generating and filtering the event is negligible. So far, we have answered all the questions in the system design. In January 2004, we went to the Impala Research Center in central Kenya, and we deployed 7 test collars on zebras. The first picture shows how we colored the very first zebra. These 2 pictures are our human-based mobile base station. And this is our mobile lab where people are processing the data. And the last picture shows a biology professor looking at the zebra data on top of an elephant skull. So the next larger scale deployment will happen in January 2006. This graph shows you the position data for 3 different zebras over a map of 5 mile to 5 by 5 miles. From the preliminary data, the biologists have found that zebras make significant movement at night, which was didn't expected. And they actually prefer the wooded area and gullies at night too. From the engineer's perspective, we found lots of interesting issues. For example, for energy efficiency reasons, it's very preferable to have opportunistic communication whenever 2 zebras meet, instead of having the zebras always wake up at the same time only once every 2 hours. And also, it would be nice to be able to reconfigure some of the system parameters, such as the sensing and communication frequency and the interval for the sensing device to be activated. And also, we would like to have more diagnostic information coming out of the tracking colors so that we can remotely monitor the detailed performance of each color. In terms of future work, for the thesis, I will migrate the adaptation and update part from the IPAC's prototypes to the real ZebraNet hardware node. And for the entire project, we plan to add more things in the middleware layer that will support automatic software reconfiguration, remote system monitoring and diagnosing, and we would like to have application input for device and power management. To conclude this talk, we have built a layered system architecture with clean interfaces for the low capability and resource-constrained sensor applications. Currently, the system consumes 16 kilobytes of code memory, and its static data consumes 320 bytes. We have designed and prototyped the application adaptation and update. The application can improve routing performance by 70%, and the update can reduce the number of software transmissions by 85%. We developed a unified network protocol for media access control and transport control, and can support a broad range of message models. Packet header overhead is 10%, and buffering overhead is less than 100 bytes. We have implemented reliable operation scheduling and efficient event handling for the long-term system activities. And based on quantitative data analysis, we have demonstrated a middleware and OS layer that implements a rich set of application services at very low overheads. That finished my talk.
Thanks. So you actually designed the system, and then after that went off to get some field data and did some analysis. What's the single most important lesson you have learned that might have changed your design, the original design?
Well, there are many.
That was not expected at the beginning.
Okay, so there were actually many things that we didn't expect. One critical thing we didn't expect that will affect our communication performance is the radio range. When we first tested the tracking colors in New Jersey, we tested on the vehicles, and the transmission range is about 4 to 5 miles, as specified in the data sheet. But when we went to Kenya, and when the tracking color were put on the wild animals, the radiation was greatly absorbed by the body because of the humidity of the body. And so the actual transmission range was only half to 1 mile. So that means the previous communication protocol we designed is not as efficient as we expected, because with shorter radio range, the network is more sparse and more disconnectivity oriented. So that's even further motivate our work of being able to adapt between different network protocols to pick up the most appropriate protocol for the real deployment experience.
Are the colors being modified because of this?
Sorry?
Are the colors being modified because of this? Like the antennas moved further off the body?
The antenna, the layout of the color was actually, the top part has the GPS antenna because it needs to face the sky. And on the sideway, we have the radio antenna. So I think this radio transmission range will not affect how the radio antenna is positioned, but rather how aggressive we want to perform the transmission, how frequent is that, how much data duplicate copies we want to put in the network.
You said there's almost a factor of 10 difference between what you measured in mobility between that and when you put it on the collar. So evidently it was not engineered to be put on a high water content body.
Yeah.
So my question is, are they
Oh, the color
re-engineering?
itself.
Are they re-engineering the collar to account for this? Like move the antenna physically a little bit further away from the animal?
Yeah, that's very true. Actually, we are going to put on, before we only have one layer of butyl for the color, but now we also have another layer of leather to prevent for humidity prevention. And also, we're also adding better waterproofing packaging in the system. So there's gonna be a lot of changes in the color design. Another change would be we realized that the colors can rotate, even if it was put very tightly on the zebra's neck, so that the GPS antenna will not receive signal after some time, but it may rotate back after more time. So a better design would be to have a V-shape color. We have a very soft and loose part on the top so that it stays as a drop, water drop. That way it's more stable in that position.
I guess when they lie down, like, they'll not be put in the sky.
Yeah.
You could have redundant antennas, right?
That's possible, yeah.
So one thing I was curious about was you mentioned that one of the things the middleware layer was doing was protecting access to the devices from the application layer. You're kind of providing kind of an OS boundary layer there. What kind of failures or what kind of things were you protecting it against? Were you protecting against one application failing? You want to keep the other ones running, or?
Yeah, that's one thing we want to protect. For example, if I mentioned that we want to adapt to the device failures. If one device fails and the current running application depends on using that device, maybe we want to switch to another application that does not depend on the same device. So that's one prevention. Another one is basically we want to protect the applications from illegal use of the devices. For example, when the system is at low power mode, everything is shut down. If the application tries to read from the flash memory, it would occur failure. It would generate failure.
The idea is to prevent, is to encapsulate knowledge about how to use the hardware safely so that if an application writer makes an error, it won't be catastrophic for the hardware.
Yes.
Okay.
If you could get the zebras to behave any way you want them to, what would you rather have them do? Walk in a group all the time, or
stand next to a base station?
Currently, the way we color the zebras is that they are walking in herds. Each herd has a leader, sort of, like a male and several females. And there is also bachelor groups. So we also only color one zebra out of a group because that could be representative of the movement of the whole group. So that's not really a way we prefer how the zebras move, because that's what the biologists want to study. But we would like to see them maybe have more interactions so that we have more data from the multi-hop peer-to-peer communication rather than direct transmission from one zebra to the base station.
You can imagine that the choices you make about communication might bias the samples that actually occur. So what feedback do you provide the scientists about when data was collected and when it wasn't, because you threw it out or because it was it was discarded for some reason, so that they can account for the observation bias?
Can you repeat the beginning?
Okay, so the choices you make about which data to throw out and which data to transmit will affect which data the scientists ultimately collect.
Yes.
So it could cause some bias in the data that they're trying to use to draw conclusions. So, for instance, they might discover that zebras like the sunshine, well, only because the zebras who aren't hanging out in the sunshine are, their batteries are running out and they're not transmitting. So, so how are you? What metadata are you providing to the scientists so that they can see which data were thrown out or lost?
We actually, we have a way to compress the data and to record the missing GPS positions. Also, that's from the raw data itself. For example, the GPS, when it records several locks, it also records what locks has been missing each time it wakes up, so that the biologist will have an idea of which data is actually missing when it's first obtained by each tracking color. But there's also data that is intentionally evicted by our communication strategy. That part we haven't looked at yet. But it's good to provide this kind of way to assist the biologist to understand more about the behavior. One thing that I want to mention is that we are looking at some similar strategy that can make the data more representative to the zebra movement. For example, we realized that most of the data was actually got at night because during the day the solars got enough sun and the voltage is high enough, so at night they can start communication and sensing. But during the day, it has been after one night, there's no energy resource. So the day activity is much less than the night activity. So we're looking at these issues about how we can distribute the system activity not based on the actual energy resource.
So let me try to understand the model here. You talk about being able to support multiple applications, but all the applications, if I understand correctly, are all trying to do the same thing, just different ways. They're all trying to get the data from out there to in here.
That's right.
Okay, so if they have varying strategies, it would seem that since they're all trying to do the same thing, that they might well conflict with one another. I mean, if one, I'm thinking of this example you just gave, and it seems like one reasonable application strategy might be to conserve power, and spend your power budget so you get better, samples distributed throughout the day. And to do that, you kind of have to be the only application on the system, because if somebody else comes along and burns up all your power at night, then, to what extent do you want to support competing applications? I mean, it seems like there's really only one application here, and you just have different ways of running it.
Right now, we haven't looked at that part. But because our assumption here is that all the applications are collaborating to achieve the same goal. But as you said, they may have conflicting strategies, and being able to...
It seems like they're competing, not collaborating. I mean, it seems like if you I guess in what sense are they collaborating, right? Because they're all you're trying to find the one that has the best strategy.
We're trying to find out the one that is best for the local network condition. Like when zebras are clustered, I may use this one. But for me, I'm the zebra, I may walk to some other place, and at that time I may use a different protocol.
All right. I think let's wrap up this. Thank you again for the talk.
I just ask a couple of questions.
Sure.
These sessions